radiation in space. The solar radiation, H naught in watts per meter square, is the power density incident on an object due to illumination from the sun. At the sun's surface, the power density is that of a black body, about 6000 Kelvin, and the total power from the sun is the value multiplied by the sun's surface area. However, at some distance from the sun, the total power from the sun is now spread out over a much larger surface area. And therefore, the solar irradiance on an object in space decreases as the object moves further away from the sun. The solar irradiance on an object at some distance d from the sun is found by dividing the total power emitted from the sun by the surface area over which the sunlight falls. The total solar radiation emitted by the sun is given by sigma T raised to 4, according to Stephen Boltzmann law. Multiplied by the surface area of the sun is 4 pi r square sun, surface area of a sphere, where r sun is radius of the sun. The surface area over which the light from the sun falls will be 4 pi d square, where d is the distance of the object from the sun. Therefore, the solar radiation intensity H naught in watts per meter square incident on an object is H naught is equal to R square sun upon D square into H sun, where H sun is power density at the sun's surface in watts per meter square as determined by Stephen Boltzmann's blackbody equation. R sun is the radius of the sun in meters and D is the distance from the sun in meters. The table shows the standardized values for the radiation at each of the planets. Extraterrestrial radiation. It is useful to know the spectral distribution of the extraterrestrial solar radiation, that is, the solar radiation that would be received in the absence of the atmosphere. The actual power density or extraterrestrial radiation varies slightly since the distance between the sun and the earth changes as the earth moves in its elliptical orbit around the sun, and because the sun's emitted power is not constant. An equation which describes the variation throughout the year just outside the earth's atmosphere is GD is equal to GSC 1 plus 0.033 cos into 360 n upon 365, where GD is equal to extraterrestrial, that is outside the atmosphere irradiance on a plane perpendicular to the sun's rays, watts per meter square. GSC is equal to the solar constant 1367 watts per meter square. N is equal to the day of the year, that is for January 1, it will be N is equal to 1. A standard spectral irradiance curve based on high altitude and space measurements is shown here, which is found to be similar to the 5500 Celsius black body spectrum. From this figure, following observations are made. The peak solar intensity is 2028.8 watts per meter square at a wavelength of 0.48 micrometer. The solar spectrum varies from 0.2 to 3 micrometer. The energy in various spectral ranges is as follows. Solar radiation intercepted by the Earth. The intensity of the solar radiation reaching us is about 1367 watts per square meter. This is known as solar constant. It is important to understand that it is not the intensity per square meter of the Earth's surface, but per square meter on a sphere with the radius of 14 lakhs 95,963 kilometers and the Sun at its center. The total solar radiation intercepted by the Earth is the solar constant multiplied by the cross section area of the Earth. If we now divide the calculated number by the surface area of the Earth, we shall find how much solar radiation is received on average by a square meter of the Earth's surface. The formula for this is R is equal to S pi r square upon 4 pi r square, which will be equal to 1367 upon 4, which will be equal to 341.75, that is approximately 342 watts per square meter, where S is the solar constant in watts per square meter and R is the Earth's radius.